Every physics textbook on Earth says Ohm's law is universal. Push electrons through a wire. Voltage equals current times resistance. Simple. Settled. 170 years old. In February 2016, 2 teams published papers on the same day, same journal. Back to back, they killed that rule. Inside a flake of graphene, the stuff of pencil lead, electrons stopped behaving like electrons. They flowed like water. They formed whirlpools. Current ran backwards against the voltage pushing it. And last September, a team in Bangalore caught those electrons cheating the textbook by a factor of 200 times. Not 2 times. Not 10 times. 200. This is the Dirac fluid. And the same equations that describe it also describe the first microsecond after the Big Bang. Here's what we're going to do in the next 10 minutes. I'm going to show you how a material 1 atom thick broke the oldest rule in electricity, how a Harvard grad student alone at 3 in the morning watched physics change on an oscilloscope, how string theorists accidentally gave us the math for pencil lead, and how a chip smaller than your fingernail became a window onto the hottest soup the universe has ever made. By the end, you'll look at a battery, a wire, a phone charger, and realize the physics inside was a polite approximation. The real story is wetter, and stranger still. To understand what was broken, you need to meet the rule. In 1827, Georg Ohm wrote V equals I times R. It became the F equals MA of electricity. In 1853, Gustav Wiedemann and Rudolf Franz noticed something even stranger. In every metal they tested, copper, silver, gold, the ratio of heat flow to electric flow was the same, always. In 1872, Ludwig Lorenz turned it into a constant, the Lorenz number, 2.44 times 10 to the minus 8, a tiny number that rules every wire on Earth. The picture was clean. Electrons inside a metal behave like marbles in a pipe. They bump into impurities. They bump into vibrating atoms. They roll independently. Each one minds its own business. Heat flow and charge flow stay proportional because they share the same marbles. Simple, elegant, universal. For 163 years, nobody saw a single exception. But there was a prediction from 1963 that nobody could test. A Soviet physicist named Rady Gorgy wrote, "If electrons ever collide with each other more than they collide with anything else, they will flow like a fluid." One small problem: no material on Earth was clean enough to prove him right. For 50 years, Gorgy's fluid stayed a ghost in the textbook. Here's where the story escalates. Because the ghost only needed one thing: a pure material. In 2004, Andrei Geim and Konstantin Novozhelov peeled a single layer of carbon off a block of graphite with Scotch tape. Graphene, it won them the Nobel Prize 6 years later. But graphene had a weirder secret. At one specific energy, called the Dirac point, electrons inside graphene stop behaving like ordinary electrons. They act like massless relativistic particles. They obey the same equation Paul Dirac wrote in 1928 for particles traveling near the speed of light. Pause on that. You're holding a piece of pencil lead. Inside, some electrons think they are photons. By 2012, researchers learned to sandwich graphene between 2 atomically flat sheets of boron nitride. The sample became so pure that an electron could travel 1 million atoms without hitting a single defect. For the first time in history, Gorgy's fluid had somewhere to live. At Harvard, Philip Kim's group started building these samples in 2012. Meticulously, 4 years of sample engineering, 4 years of inventing new thermometers, 4 years before the data was solid enough to believe. In Manchester, Andrei Geim's group was hunting a different prediction. A theorist at MIT, Leonid Levitov, had written something outrageous in the summer of 2015. He claimed that if electrons became a fluid, they should form whirlpools, tiny tornadoes of charge, and those whirlpools should drive current backwards against the voltage. Physics 101 said that was impossible. Levitov said, "It's already happening. You just haven't looked." Picture a basement at Harvard. 3 a.m. The temperature of the sample reads 1/100th of a Kelvin. That is colder than the vacuum between galaxies. A grad student named Jesse Krasno is watching a number. For 6 weeks, the refrigerator has been cooling. 6 weeks of continuous patience. In his dissertation, he would joke that dilution fridge patience was the skill he leveled up most in his PhD. Krasno had built something extraordinary. A Johnson noise thermometer that could measure temperature to 5/1000ths of a degree in 1 second, precise enough to hear the whisper of heat moving through electrons. He pulls up the data, the ratio of thermal conductivity to electrical conductivity, the sacred Lorentz number. It is off by a factor of 10. 10 times too much heat for the same current. The Wiedemann-Franz law, unbroken since 1853, was lying on the floor. Meanwhile, 5,000 kilometers east, in Manchester, a PhD student named Dennis Banderin is also staring at an oscilloscope. He has been running routine tests on a graphene device. The voltage reading in one specific spot is negative, not zero, negative. Physics 101 says current flows in the direction of voltage. Water flows downhill. In Banderin's sample, it was flowing uphill. Neither team knew the other existed. On February 11, 2016, the journal Science published 2 papers back-to-back. Krasno and Kim in one, Banderin and Geim in the other. 2 coasts, 2 experiments, 1 conclusion. Electrons in the right conditions are liquid. Let's sit with what that means. When water flows through a pipe, it doesn't move as a block. The water in the middle moves faster. The water near the walls drags. If you narrow the pipe, you get turbulence, whirlpools, eddies. This is Navier-Stokes, the math of fluids. In 2016, the Manchester team measured the viscosity of electrons in graphene, 0.1 square meters per second, 100 times more viscous than honey. Honey-thick electrons in a piece of pencil lead. The whirlpools Levitov predicted were real, 0.5 micron across. Swirling tornadoes of charge, invisible to any normal microscope, and the reason the voltmeter read negative in one spot. The vortex was literally dragging current against the flow. Then, in 2019, a team at the Weizmann Institute did something nobody thought possible. They photographed the flow using a single electron transistor mounted on a carbon and nanotube tip. They mapped the velocity profile of electrons inside a graphene channel. It was a parabola, the exact parabola you get when water flows through a pipe. Poiseuille flow, drawn in 1840, redrawn 179 years later by electrons in a carbon sheet at 5 Kelvin. In 2020, a second Harvard team, using quantum diamond sensors, took the same picture at room temperature. Room temperature. You could, in principle, hold the Dirac fluid in your hand. Now the story gets genuinely strange. In the late 1990s, a theoretical physicist named Juan Maldacena wrote down a bizarre duality. Certain kinds of quantum fluids, he claimed, are mathematically identical to certain kinds of black holes. String theory on one side, fluid mechanics on the other. The same equations. From this idea came a prediction, a lower limit on how frictionless a fluid could ever be. The KSS bound, viscosity divided by entropy density, greater than Planck's constant over 4 pi k b. No real fluid could be perfectly slippery. But the bound said, something close exists. Somewhere. Then the physicists at the LHC and REAC found it. When they smashed lead nuclei together at near light speed, They created a soup called the quark-gluon plasma, the primordial matter from the first microsecond after the Big Bang. 4 trillion Kelvin, hotter than the inside of a star, and its viscosity almost saturated the KSS bound, the most perfect fluid we'd ever seen. Until September 2025, at the Indian Institute of Science, a team led by Arindam Ghosh and a first author named Aniket Majumdar published a result in Nature Physics. In ultra-clean graphene, the Wiedemann-Franz violation didn't peak at 10. It peaked at 200. Majumdar put it like this, and I'm quoting him directly. Since this water-like behavior is found near the Dirac point, it is called a Dirac fluid, an exotic state of matter which mimics the quark-gluon plasma, a soup of highly energetic subatomic particles observed in particle accelerators at CERN. Let that settle. The same equation rules 2 fluids. One of them is the hottest thing humans have ever made at 4 trillion Kelvin. The other is at 5 Kelvin, inside a chip on a desk in Bangalore. 12 orders of magnitude of temperature, 1 underlying math. Graphene is, in a very real sense, a tabletop Big Bang. So, what does this change? Look at your phone. Every chip inside it is designed with Ohm's law. Every GPU training, every AI model, every transistor in every electric car. They all assume electrons behave like marbles. That assumption is a simplification. A beautiful, useful, century-and-a-half-old simplification. And it's starting to break. As chips shrink, 3 nanometers, 2 nanometers, sub-1, the electrons inside them have nowhere to scatter. They start to see each other. They start to flow. Engineers are quietly learning that tomorrow's transistors may have to be designed with fluid dynamics software, not circuit theory. Meanwhile, the Dirac fluid is already growing teeth. Thermal amplification in these materials means a tiny signal becomes a measurable one. Jesse Krosnow, the Harvard grad student, now builds quantum sensors at a lab called Raytheon BBN. The IASIC team is prototyping single-photon magnetometers, sensors that might detect 1 spin in a brain, 1 axion of dark matter, 1 photon from the edge of the universe. All of it because 2 teams, on opposite sides of the world, decided to trust a weird reading on a weird Tuesday in February. I want you to hold one thought for a moment. A flake of graphene is thinner than anything you can see. It is literally the edge of what carbon can be. 1 atom. That is all. And inside that 1 atom of thickness, the universe runs the same math. It ran in its first microsecond. The same math that rules black holes. The same math that rules the hottest matter ever made. You are not separate from any of this. The carbon in your pencil is the same carbon in your cells. The rules that broke in graphene are the rules that govern every wire in your pocket. The universe is not out there. It is stitched through every ordinary thing you touch. Next time you pick up a pencil, remember, somewhere in the smudge on your fingertip, electrons are trying to swim. Under the right conditions, they would. 1 law broken opens the door to others. For 2 centuries, physics taught that perpetual motion was impossible, that anything that moves must lose energy, that nothing, inside a closed system, can tick forever. In 2012, a Nobel laureate named Frank Wilczek asked a question nobody had dared to ask. What if time itself could crystallize? What if matter could arrange itself not in space, but in motion, and repeat without ever slowing down? The community laughed. Then, in 2016, a team at the University of Maryland built one, a crystal that oscillates forever in the ground state. No energy added, no energy lost. A violation of time translation symmetry. A clock that cannot stop. And it's still running. Title suggestions. 5 options. Glop 1. The 170-year law broken by pencil lead. 58 chars 2. Electrons learn to swim. in pencil lead, 44 chars. 3. Why electrons flow like water in graphene, 42 chars. 4. A chip on a desk that mimics the Big Bang, 43 chars. 5. 200 pies broken, the law every textbook gets wrong, 49 chars.